Hello everyone, I am Sujata Moril. Welcome you all in the video lecture on the topic numerical methods. Solution of ordinary differential equation Euler's modified method. Numerical solution of first order first degree differential equation which is given by equation 1. An initial condition which is given by equation 2 y of x naught equal to y naught. We solve this equation 1 by four different methods. Taylor series method, Euler's modified method, Runge-Kutta method, Milne's predictor corrector method. Then there are so many methods, Picard's method and so on. But in this video, we are going to discuss second method, that means Euler's modified method. Now for solving the first order first degree differential equation, we apply this Euler's modified method. For this, first we are to find out y1 value by using the Euler's formula. That means equation 1, y1 equal to y naught plus h function of x naught y naught, which is called predictor. Here x naught and y naught which is given in the condition. H is the small value which is also given in the condition, otherwise we can find out by the finding value. Then we substitute this y naught, h and function of x naught y naught and we find out the value of y1. Then the first modified value of y1 is y1 of 1 equal to y naught plus h by 2 function of x naught y naught plus f of x naught plus h y1. Now here x naught plus h we can write down as x1 or x naught plus h and we call this as corrector value. Now this corrector value also we find out by using the formula. Here y naught is already given, h is already given, function of x naught y naught and function of x1 y1. We substitute all these values and find out y1 of 1. Similarly, we find out the y1 of 2. Only difference in the formula is last term here function of x1 y1. Instead of this we write down x1 y1 of 1 and continue this process till the two consecutive values of y1 will agree. Then we find out y2 again with the same procedure till the desired degree of accuracy. This is the first iteration. After first iteration, we find out the value of y1 for x1. If we had to find out y2 value, then again apply same method, make the changes accordingly and find out the value of y2, then y2 of 1, y2 of 2 and so on and finalize the value of y2 for x2. In this way, we apply the formulas and find out the required result by Euler's modified method. Now we discuss the problem on this method. Use Euler's modified method to solve the equation dy by dx equal to x plus y for x equal to 0.1. You are given y of x naught equal to y naught, that means x naught value is 0, y naught value is 1, h equal to given 0.05. Now we know that here x1 equal to x naught plus h. Here x naught is 0, h is 0.05, that means x1 is 0.05. That means we get the value of y1 for this x1. This is the first iteration, but we have to find out value for x equal to 0.1. Therefore, x2 equal to x1 plus h. We substitute the value of x1 and h, we get 0.1. Therefore, we find out y2 value for x2 equal to 0.1. In this way, we find out two iterations here. After first iteration, we get y1 value. After second iteration, we get y2 value. Now, here x naught 0, y naught 1 and h equal to this. Function of x1 means the right hand side of the equation, x plus y. Now for this we find out f of x naught y naught, that means f of 0 and 1, then its value 1. That means we substitute x equal to 0 and y equal to 1 in this equation, x plus y, we get the value 1. Now we substitute this value in predictor formula by using Euler's modified method. This is the equation number 1, which is the predictor formula. We substitute the values y0 is 1, h is 0.05 and function of x0 y0 is 1. Then we get y1 is 1.05. Now we find out the y1 of 1. That means modified first approximation of y1. y0 plus h by 2 function of x0 y0 and plus f of x1 y1. x1 means here x0 plus h. Here f of xy is x plus y. Then we easily find out f of x1 y1. x1 is 0.05, y1 is this equation number 2 value, that means 1.05. We added this, then we get 1.1. We substitute this value here and x0 y0 function of x0 y0 is 1. Substitute all these values, we get the y1 of 1 is 1.0525, that means equation number 4. Now y1 of 2 equal to this formula here, function of x1 y1 of 1. Here this is the change, therefore here we find out value of function of x1 y1 of 1. x1 is 0.05, y1 of 1 is 1.0525. Its value is 1.1025. We substitute this value in the last term of the equation number 5. And then we get y1 of 2 equal to 1.0525. y1 of 1 is 1.0525 and y1 of 2 is also same value. Therefore, we stop the iterations here and we get the final value of y1 when x1 equal to 0.05. After first iteration, final iterations, we get y1 value for x1 equal to this, but we have to find out the value of y for x equal to zero point 0.1. Therefore, now we start the second iteration. Here we make the changes in the formula y2 equal to y1 plus h function of x1 y1. Now x1 is 0.05, y1 is 1.0525. Substitute here value. This value we substitute in the equation 8 second term, and then we get 1.1077. Now find out y2 of 1 by substituting the values, and here we have to find out f of x2 y2, which is find its value equal to 1.2077. Substitute here, then we get 1.1102. This is the equation number 10. Now if we find out next value y2 of 2, its the value is 1.1103. The difference between these two values is less than 0.0005. We can stop the iteration, and if we find out the next iteration value, we get the same value. y2 of 3, we get same value, therefore y2 equal to 1.1103 when x2 equal to 0.1. In this way we find out the values of y when x equal to any given value. Differential equation is given, then we easily apply Euler's modified method. These are the examples. Now here dy by dx equal to this value. This is the function of xy, and here x not equal to 1, y not equal to 2 and x equal to 1.2, h equal to 0.2. Now we x1 equal to x naught plus h, therefore 1.2. Here we have to find out this value. For this value we get y1 value, therefore we have to do only one iteration here. In this way we decide the how many iterations we have to do for finding the required result of the given problem. Now, these are the practice problems. Thank you.